right, good morning guys. So today we're going to be moving on to sort of our next topic. So we spent the last 2 days talking about the different sides of our right triangles. Okay, so I just wanted to do a quick refresher on that before we get into our next topic, because our next topic is getting into those trigonometric ratios, so trig ratios, that I've been mentioning as we go through this. So it's really important to understand how to label your triangles. Okay, so knowing which side's the hypotenuse, and then how we label the adjacent and opposite sides relative to a specific angle. Okay, especially moving forward when we use these trig ratios, they're based on the sides of our triangles. Okay, and they're specifically based on the labels that we give them. So you'll see what I'm talking about a little bit later on today when we start doing some examples. We're going to start with just one of the trig ratios, which is going to be sine theta. Okay, so we'll get into what all of that is. But first, let's just do a quick refresher on our hypotenuse, adjacent, and opposite sides. Okay, so remember again, when we're talking about our trigonometry, moving forward, we're only going to be focusing on right triangles. Okay, so those triangles that have that right angle, which is a 90-degree angle in them. We've shown back at the beginning of our unit how we can use the Pythagorean theorem, which is this guy up here. Okay, we've shown how we can use that to determine whether or not a triangle is right angled. Okay, so remember, if you plug all of your information into the formula, so C is going to be your longest side, and then A and B will be your two shorter sides. So if you plug that information into your Pythagorean theorem, you solve both sides of the equation. If the numbers on both sides of the equation are the same, then this is a right triangle. Okay, the triangle that you're trying to determine, it is a right angled triangle. If the numbers on both sides of the equation are different, then you are not dealing with a right angled triangle. Okay, so that's one way that we've seen using it. We've also seen how we can use the Pythagorean theorem to find the missing side of a triangle. Okay, so specifically we were using it to find the hypotenuse. Okay, I think we might have done a couple of examples finding sides A and B. Okay, but we can see how if you're given two sides, so if you're given a measurement for A and B, then you're able to solve for side C, right? Because then you only have one unknown. And how did we do that? So just a quick refresher on that. You have A squared plus B squared equaling C squared. Okay, that's just our Pythagorean theorem there. If you know what A is, so let's just say that A is whatever number, B is whatever number, and then C is our unknown. You solve for these, so we would do x squared and y squared. We would figure out what that equals, and then we'd find out what they equal together, so we'll just call it xy equaling C squared. Okay? And then the hardest part of solving for this equation is just remembering how to solve for C. So remember that whatever answer you get for C squared is not your final answer. The side of the triangle, so the hypotenuse, is called C. Okay, it's not called C squared, it's just C. So that means that we need to solve for our variable by getting rid of that exponent. So remember when you're solving for equations that if you want to get rid of something, you just do the opposite operation. So as an example, if C was being multiplied by something, to get rid of that something, you would divide it. Okay, if you were adding something to C, if you wanted to get rid of that something, you would subtract it. So all we're going to do to solve for this is the opposite operation. So the opposite of squaring something is taking the square root. Okay, so square root, it sort of looks like that, right? So square root just means that we're getting rid of that exponent. So when you take the square root of something, you're getting rid of this exponent too. Okay, so if we do that to one side of the equation, remember that equations always have to be balanced. So if you do it to one side of the equation, you have to do it to the other. So we would take the square root of our number on the left side, and then we would get our answer. So whatever it would be, right? It would be whatever the square root of xy is. Okay, so that's how we use the Pythagorean theorem to solve for missing lengths in a right triangle. Okay, so we've seen two applications of it so far, using it to determine whether a triangle is right angled, and then using it to determine missing lengths. Okay, so Pythagorean theorem is really heavily focused on the side lengths, right? We weren't really talking too much about angles. The only time it really ever came up was when we were just mentioning that it was a right angled triangle. Okay, So when we get into these trig ratios, you're going to see that we're combining the lengths and the angles. So that's why we're trying to sort of get an understanding of them separately before we bring them together. So beginning of the unit, we started by talking about the angles inside of a triangle. And remember that those always add up to 180 degrees. Okay. What else did we talk about? We talked about the different types of angles. So acute, obtuse, reflex, straight, and right angle. Okay. So those are all things that we went over last week and what we've seen for applications of trigonometry so far. Okay, so then the last 2 days we were talking about the different sides of the triangles. So remember that when we're using the Pythagorean theorem, we said that the longest side, so the side with the biggest measurement, was always our side C. Okay, it didn't matter between the two shorter sides which one we called A and which one we called B, as long as we said that the longest side was side C. Okay, so then we wanted to know, well, why is that? Why is this side so important? So side C, the longest side, is also called the hypotenuse, right? So the hypotenuse has two identifiers, so it's the longest side, and it's also the side that is opposite the right angle. So it's directly across from that right angle. Okay, hypotenuse is the one side of our triangle that's always consistent. In any right triangle, it's always going to be the same thing. It's always going to be your longest side, and it's always going to be directly across from the right angle. Then we have these two other sides. We have the opposite and adjacent sides, and remember, these ones are a little bit tricky because they change. So opposite and adjacent sides are labeled relative to a specific angle. Okay, so in a triangle, depending on which angle you're talking about, your bottom side might be the adjacent side and the right side might be the opposite, just like in this example here. But if you were talking about a different angle, so if you're talking about some sort of angle that was up here, okay, in that case, this one here would be the opposite side, and this side here would be adjacent. So we have to remember what these two things mean. So opposite is pretty intuitive. So opposite just means the side that is opposite or across from the angle we're talking about. Adjacent is just a different way of saying next to or beside. Okay, so the adjacent side is going to be the one that is right beside the angle you're talking about. It's actually going to be one of the sides that makes up that angle. Okay, so you can see in this example here, if this was the adjacent side to the angle theta that I just drew, you can see that this side is contributing to this angle, right? It helps make up that angle. Okay, so opposite and adjacent, and notice the hypotenuse does not change no matter the angle we're talking about. The hypotenuse is always opposite from the right angle, so it never changes. Okay, so that's what we talked about the last couple of days. Did a couple of different examples here. So again, just seeing how when we're talking about the angle being in this corner, you know, we have the opposite side being the one on the left here and the adjacent being on the bottom. Then if we looked at the same triangle, but we were talking about the angle up here, okay, so up in the top corner, then all of a sudden our side on the left becomes the adjacent side and the one on the bottom becomes the opposite. Okay, so we just went through a couple of examples of doing that, just looking at the same triangles but relative to different angles. So if you guys are having any trouble with that, definitely read back through these notes and just look through the examples that we did. The other thing that we mentioned where we introduced these two Greek letters, so remember that this one here, the sort of fancy O, is called theta, and then this little fish looking or fancy A is called alpha. Okay, and those are just Greek letters that we commonly see in math to represent, usually they represent angles. They come up in other types of equations, especially in physics, sometimes in chemistry and things like that. So definitely big in the sciences. And then for math, we usually just use them to represent angles. Okay? Okay, so let's move into talking about the first of our trig ratios here. So I told you that the first one we're going to talk about is called sine theta. Okay, so let's just look at this example here and then sort of talk about what all of this means. So triangle ABC, okay, so triangle ABC, that's going to be this one here, okay, ABC, is drawn inside triangle ADE. So let's just switch colors here. So ADE is going to be ADE. So these letters here just represent the corners of the triangle, okay? So we have a triangle ABC, and then we have the bigger triangle ADE. The two triangles are similar, so this means that they have equal angles, okay? Equal angles mean that, well, obviously they're both right triangles, so they both have this 90-degree angle, but then they're also both going to have the same angle here, as well as here and here. Okay, so they have two angles in common, right? They have this 90-degree angle here. Angle A, so the one in this corner here, right? That's the same for both of the triangles, right? It's part of triangle ABC as well as triangle ADE. Okay, so two of the angles in these triangles are the same, which means that these ones here must also be the same, right? Because if we remember our rule that all of the angles in a triangle must add up to 180 degrees, then we know that if two of them are the same, then that third one must also be the same, because there's only going to be one number that you can add to the other two that will equal 180 degrees. Okay, so similar triangles are going to be triangles that they might have different side lengths, right? We can see that ADE is much bigger than ABC. They have different side lengths, but they have the same angles. So what we're going to do is we're going to find their sine ratio. Okay, so a sine ratio is determined by dividing the length of the opposite side of the triangle divided by the hypotenuse. Okay, so this is where being able to correctly label our sides becomes really important. Okay, notice that in our equation here, so we're doing opposite over hypotenuse, we're not involving the adjacent side at all. So if we mix up our opposite and our adjacent sides, then we're going to get a different answer. We're going to get the wrong answer. Okay, so remember back from when we learned ratios, which would have been in, I believe, AB 3-4, maybe even 1-2, or whatever course you've taken before this one. Okay, a ratio is just sort of a relationship, right? It sort of represents a relationship between two things. So we're going to divide the opposite side by the hypotenuse. And for this triangle, so we have these two triangles here, ABC and ADE. Okay, we're going to compare their ratios and just see how similar they are. Okay, we're going to see if they're the same. So we're going to find them relative to angle A. Okay, so how do I know that? Because it says here we're going to find the value of the ratio opposite side to angle A over hypotenuse. Okay, so we want to determine which sides are opposite from angle A. So angle A, and again, I'm just going to switch colors here to make it more obvious. This is going to be angle A right here. Okay, so we need to figure out the opposite and hypotenuse sides for both of our triangles. So remember our definitions. So hypotenuse is easiest to label. Hypotenuse is your longest side. So let's focus on our smaller triangle. Let's focus on triangle ABC. So remember ABC, so that's going to be the smaller one here. Okay, we have three measurements. We have 3, 4, and 5. Hypotenuse is always our longest side, so this one here that's 5 units is going to be our hypotenuse. Okay, if that's the hypotenuse for our smaller triangle, it's also going to be the hypotenuse for our bigger triangle. Okay, if we look at our bigger triangle, we have to do some addition. So our bigger triangle has a measurement of 5 plus 4. Okay, we have to add these two numbers together. So our bigger triangle is going to have a hypotenuse of 9 units, okay, but it's still going to be the hypotenuse. Now we want to figure out which sides are opposite sides. So remember our definition of opposite. The opposite side is the one that's directly across or opposite from the angle you're talking about. So we're talking about angle A here. So the side that's directly across from it is going to be this one here. Okay, so this side here that's 4 units long is going to be our opposite side. Okay, so since our two triangles are similar, you can see if we do the same thing, so relative to angle A, if we extend that over here, this is going to be the opposite side for our bigger triangle. Okay, so obviously that means that down here, these bottom ones are going to be the adjacent sides. We don't really need to label them just because we're not too worried about the adjacent right now. We just want to know our opposite and our hypotenuse. Okay. So now that we've done that, we're just going to fill in our numbers. So if we look down here, we want to do our opposite side over our hypotenuse. Okay, so we want to do that for both of them. So let's just do that before we look at the answers here. So let's switch colors. Right? So for triangle ABC, so remember that's our smaller triangle, we want to do opposite side over hypotenuse. Okay? So we said that the opposite side was this one here, that's 4 units. Okay, so for opposite, we're going to put 4. Okay? Our hypotenuse is this one that's 5 units, so it's going to be 4 over 5. Okay? Now, if we divide that in our calculator, if we do 4 divided by 5, we're going to get this answer of 0.8. Okay, so 0.8 is the ratio of the opposite side to the hypotenuse for our smaller triangle. Now we want to do the same thing, but we're going to do it for our bigger one. So we're going to do it for triangle ADE. So let's just get rid of this here. So we want to do it for triangle ADE, so our bigger triangle. Okay, so opposite over hypotenuse. Okay, so the hypotenuse, right, that's going to be our bottom number. So hypotenuse, remember we had to add these two numbers, so we have 5 plus 4, so our hypotenuse is 9 units long. And then for our opposite side, we see that it's 7.2. Okay, so 7.2. So if we divide these numbers, so 7.2 divided by 9, remember that when you have a fraction like this, or when you write it like this line just means divide by. Okay, and I know that's not getting cut off by my screen here. Okay, so 7.2 divided by 9. If we do that, we actually end up getting 0.8. So 0.8 is the ratio of the opposite side to the hypotenuse in our big triangle as well. Okay, so if we compare them here, we can see that these triangles, even though they have different side lengths, they have the same ratio. Okay, you can see they did the same, calculations here, right? They did opposite over hypotenuse for both of the triangles. Okay, and they end up getting the same numbers, right? So 0.8. So what does this mean? This means that our ratios do not depend on the size of the triangle. So the ratio has the same value for different triangles. Okay, so even though, sorry guys, I'm still fighting this cold here. Even though our triangle ABC is obviously quite small compared to triangle ADE, okay, they obviously have a pretty big difference in size, they have the same ratio. Okay, so they have the same interior angles. Remember, we talked about that at the beginning. And then they also have the same ratios. So you take two of their sides. So specifically for sine, we did opposite over hypotenuse. We get the same ratio for both triangles, even though they have different side lengths. Okay, so triangles can be similar without having the same lengths, without being the same side. So what does this mean? What we can take for this is that the ratio only depends on the angle. Okay? It doesn't depend on your side lengths at all. It only depends on the angle. So the ratio that we just calculated, so opposite over hypotenuse, that ratio is called sine theta. So this SIN here, that stands for sine. Okay? So our formula for sine theta, so we call it sine theta when we're referring to angle theta, okay? Sine theta equals opposite side to theta, okay, so that's our angle of reference, divided by hypotenuse, and hypotenuse is always the same, okay? You can have different types of sine ratios, so we are talking about sine theta specifically in this example because our angle was called, well actually up here it would have been sine A, right, because our angle was A. But when we're talking about a ratio in relation to angle theta, we call it sine theta. But notice in this example down here, we have sine theta and we also have sine alpha. Okay, remember alpha is our little fancy A, or if you draw it like I draw it, it's sort of like a little fish. So sine theta is going to be the ratio based on angle theta, so that one there. And sine alpha is going to be based on our angle alpha. Okay, so let's see what the difference between those two are. So first thing we want to do is label our sides. So the longest side is always our hypotenuse. So we can see that this one here, that's 13 units, is going to be our hypotenuse. Okay. Now we want to label our sides relative to angle theta. So which side is going to be opposite of theta? Well, it's going to be the one that's directly across from it. Okay. So this one here is going to be our opposite side. So if we're figuring out our ratio, our sine ratio for sine theta, okay, our opposite side is going to be 5 and our hypotenuse is going to be 13. So we divide those numbers, we get 5 divided by 13, and our sine theta ratio is this number here, 0.3846, and then there's obviously more digits, but they just rounded it off, okay? Now let's try and figure out the same ratio, but based on sine alpha. So this time we want to label our sides in relation to angle alpha. So remember, our hypotenuse doesn't change. The hypotenuse is always the longest side. It's always the side that's directly across or opposite from the right angle. So our hypotenuse is still going to be 13. Okay? But the side that's opposite of angle theta isn't going to be the same that's opposite, or sorry, the side that's opposite angle alpha is not going to be the same as the side that's opposite angle theta, right? If we draw our line and find the side that's directly across or opposite from angle alpha, it's going to be this one here. So it's going to be this one that's 12 units long. So for finding sine alpha, our opposite side is going to be 12. Our hypotenuse is still 13. So we divide those two numbers, 12 divided by 3, and we get our ratio for sine alpha as being 0.923. And again, there's more digits, but they rounded it off. Okay? So notice that there's a big difference in these numbers, right? There's about a 3 times difference. This one here is about 3 times as big as the other. Okay? That's why it's so important to understand how to label the sides of your triangle correctly. Okay? Always make sure you're checking which angle you're supposed to be referencing. So if it's asking for sine theta, label your sides according to angle theta. If it's asking for sine alpha, label your sides according to to angle alpha. Okay? Your hypotenuse is consistent, so you only have to label that once. It's always going to be your longest side. The opposite and adjacent sides will change depending on which angle you're talking about. Okay, so for sine, we weren't concerned about the adjacent side at all. We were just talking about the opposite side and the hypotenuse. When we get into our other trig ratios, okay, there's actually 3 that we're going to focus on. So sine we just learned, and that deals with the opposite side. Then we also have cosine and tangent. Okay, so those are ones we're going to get into when we get back from reading week. So you don't have to worry about them right now. I just want to mention them to you guys. And they're going to use other sides of the triangle. So instead of the opposite and hypotenuse, cosine uses adjacent and hypotenuse. And then tangent uses opposite and adjacent. Okay, so we have 3 different combinations of sides that represent different ratios. Okay, so with all of these ratios, so with sine, we can have 2 different ratios in one triangle. We can have one relevant to this angle here, and then one relative to this angle here, okay? We're never going to do one relative to our right angle. The reason for that being, if you remember, if we tried to label our sides relative to our right angle, then our hypotenuse would also be our opposite side. So it doesn't work, right? One of our sides would have 2 labels, and then the other 2 sides would both be adjacent. It just wouldn't work, okay? So in a triangle, in a right triangle specifically, there's going to be 2 different ratios. One for our bottom angle, so one for one of our angles, and one for our other angle, okay? Never for our right angle, okay? So tomorrow I have a video for you guys, a YouTube video that kind of goes over the same thing we just talked about today. So talking about this sine ratio, so sine theta. It has a couple of more examples and just kind of explains it in a different way. Again, sometimes it's helpful to hear something taught by 2 different people, just because sometimes something I say might not stick, but if someone else puts it in a different way, it's more helpful to you, right? It just depends on your learning style. And sometimes it's just a matter of hearing things more than once, okay? So I have a video of that for you guys tomorrow. A reminder that I don't have an assignment for you guys over the break, but I do have mathletics for you, okay? Again, at this point, I don't know which assignments they'll be. but they will be posted in the usual spot. So if you go to Content Library, Assignments, it'll say Mathletics for the week of October 7th to whatever day. I'm going to leave it open until the end of reading week, so feel free to work on it over your holiday. Again, I don't necessarily recommend leaving it till the end of your holiday, just because sometimes it's easier to do these things while they're still fresh in your mind, okay, but it's totally up to you. Again, if you do have any questions, I have limited Wi-Fi, so you can send me an email or send me a message on Teams, and I should get it. I just can't promise you how quickly I'll answer. So nothing should be too urgent since you don't have any assignments due while I'm away. But if you do have any questions, feel free to reach out to me. And if I don't get back to you, just don't worry about it, because we'll do a bit of a catch up when we all come back from reading week, okay? So YouTube video tomorrow, it is a really useful one. I definitely recommend coming to class if you can. If you can't, I'll post the link to it at the bottom of this lesson, or maybe if I have room. No, I don't have any room at the top. I'll post it at the bottom of this lesson. So when you guys watch this lesson, it should be down here. Okay. So if you're not going to make it to class tomorrow, not a big deal, but definitely try and watch the video on your own time. And we will do a refresher on all of this when we all get back from reading week. And yeah, so we'll get together tomorrow to do that video, and you guys have a great holiday.